Alright, let's dive into acceleration just a little bit more. This is using the same scenario before, where we had the elevator accelerating from the ground floor upwards to a top floor, which that's our, if you remember, our positive inflection sign on the position versus time graph. Forgot my labels. And then it has to decelerate a little bit, and that's why we have a little. It'll be, if it's a constant acceleration, it'll have a shape of a parabola. So that's actually a little parabolic curve right there we're just seeing a segment of. In between, we saw that we had a constant velocity. So going to our velocity versus time graph, all we had to do was literally find what's the slope right here. Let's plot it. The slope is 0. What's the slope right here? Well, it keeps getting bigger and bigger and bigger, so we need to keep plotting larger values. And then anytime you see a velocity versus time graph where it is flat, looking at this spot right here, that would correspond to the position versus time graph where you have a constant slope. And then once again we decelerate or turn around and start accelerating in the opposite direction so we can come to a stop. And our position may be way up here on the top floor, but we still have a 0 velocity. So just know how to go between these two graphs. And now let's talk about how we get that acceleration graph. First of all, we saw before that average velocity was equal to x final minus x initial over t final minus t initial, or the change in position over change in time. Well, we get the same thing for acceleration, except it's the change in velocity with respect to time. And we can take the limit definition as delta t goes to 0 of delta v delta t, and that gives us our calculus definition for the rate of change of velocity with respect to time, and that's acceleration. So we need to know this. We're going to use it to get to some kinematic equations, as well as velocity is equal to dx dt. Very important definitions. Okay, so how do we know we can get from position to velocity graphs by literally just finding what the slope is and then plotting it to the corresponding time. We can go one step further and find the acceleration. Well, by definition, this literally just says that it is equal to the slope of the velocity versus time graph. So that's what we're going to do. Right here we have it turns out a slope of +2 for this section. And we can literally just go up here and say, alright, well, it accelerated at a constant 2 meters per second squared. It initially was at rest and stayed there till 1 second, so it had a 0 acceleration. When you see something flat or with a 0 slope, that's going to indicate that there is no acceleration. So we have one of those sections down here, and another one up here, and another one here. That means during this interval, there's no acceleration. Now you might notice that this slope is negative and a little bit steeper than the one on the left. Well, that means it is coming to a stop more rapidly than it accelerated in the beginning. It has, the magnitude of its acceleration is greater. It's just in the other direction. So how do we represent that? Well, we just come down here on the negative scale. If that was 2, I believe this one is to -4. And plot some points. Ta-da! And remember here, that's sitting on at a 0 velocity, and it's not has a 0 slope. That also means that there's no acceleration. So we just turned a position versus time graph into a velocity versus time graph into an acceleration versus time graph. What kind of sensations would you feel when you're in this elevator? Well, when it's pulling you up, it's going to make you feel heavier. You're going to feel squished. When it starts dropping down in the other direction, you may actually get a little taller and feel a little bit elongated because less gravity is going to be acting on you. Well, the same amount of gravity, but since you're going in that direction, you get a net effect of less G's on you. And what do I mean by G? 1 G is equal to 9.81 meters per second squared. That is the acceleration due to the force of gravity on the surface of Earth, and it's an average. If here's the surface of Earth and you went below sea level, it's going to be different. If you went to the top of Everest, you are actually going to be a little bit lighter. And we'll go over the laws of gravitation and why that value changes later in this semester. But for right now, know that if we speak of G's, we are talking about 1 G equaling 9.81 meters per second squared. If something was 3 G's, we get about 29 meters per second squared. Okay. Also, it should be noted, if we can get acceleration as the derivative of velocity with respect to time, doesn't that also equal the second derivative of position with respect to time? So what that means is if we're given a function or something in the future, like x as a function of time is equal to, I'm going to make something up, 2x to the third. We can get to velocity by taking the time derivative. So take the time derivative of the whole thing. And using your polynomial rules for derivatives, pull the 3 down, multiply it by the 2, gives us a 6, and leaves us with a 6x. Now we can go one step further, take another derivative to get to acceleration as a function of time, and our laws in this case would bring this down to a 0 power, and we'd just be left with 6. So in this case, we have a constant acceleration. The velocity, however, was not, and I should have used t instead of x. Constant acceleration doesn't, 0 is a constant acceleration, right? Just like velocity of 0 is equal to a constant velocity. So don't get confused with that. Just because, and that doesn't mean you're not moving. We can have a velocity with a 0 acceleration and still be moving. It just means that it's a constant. Okay. Just like with velocity, the sign gives us the direction, and we're going to pick that direction whenever we solve a problem. Generally, I will teach you to pick positive up and positive to the right. If your answer comes out negative, that means it's either down or left. And that it takes out a little bit of room for error, I guess. There's one last thing you have to remember. Just switch your signs at the end. If you don't have to remember that, then you're good. It just leaves one less place to make a mistake. Okay, section 2.4 in your book I'm going to do in the next video, but I'm going to mix it with 2.5 because what they're going to do is throw out all these kinematic equations that you've seen before, but they don't teach you where they get them until the next section, and that's kind of odd. So I'm gonna derive all of our kinematic equations for constant acceleration. And I want you to be able to do this too, because sometimes our accelerations are not constant, but we need to find these kinematic equations in the same manner. This will make sense after the next video, and I will definitely be assigning some problems where we have constant accelerations and non-constant accelerations. And then once we get to what causes these accelerations, which are forces, then the force might not be constant. They generally aren't. The force could be something like e to the t, or anything, right? 2x squared, or it could be a trigonometric function, cosine of t. Lots of things move like this, by the way. You'll learn that mainly in physics too. Lots of it in here though too. A pendulum, vibrations and oscillations, atoms, everything jiggles according to the shape of a sine or cosine wave. Alright, so that's what we're going to get next. We're going to learn how to derive these equations that you have seen most likely before. You just were never told where they came from. Alright, see you next time.